Hi guys, Mrs. Brumwell here. We're going to get into 2.3. This is the first part of it. We're going to talk about how to find the derivative of polynomials, the function e to the x, and natural log of x. And we're going to give you some shortcuts today. So we've been using that long definition of a derivative, the difference quotient, right? The limit as h approaches 0. And we're going to kind of look and see if we can see some patterns to use some rules, some shortcuts to help us find the derivative a little bit quicker. Okay, so let's think about finding the derivative of f of x equals 3. So remember, that is just the horizontal line through 3, right? So that is the line f of x equals 3. So if I want to find the tangent line for any points along there, the slope of the tangent line to this is going to be 0. So remember, the derivative is the slope of the tangent line at a point. So if I have something of this form, the derivative of a constant is always going to be 0. Okay? Always, always, always. Derivative of a constant, and that's why. It's because the slope of a tangent line to a horizontal line is always going to be 0. So you guys have seen the prime notation a little bit here, y prime or f prime of x. You're also going to see a decent amount of Leibniz notation, which can be seen a variety of ways. So dy dx or d dx of y, d dx of f of x. So this is an instruction to find the derivative of this function, and it kind of tells us with respect to which variable. So d dx tells us with respect to x, we're finding the derivative of the function. Operator notation, I would say this one's probably the least common, but basically this capital D is saying D is said to operate on the function and the result is the derivative. So a couple different ways we can just see that notation. Okay, all right, so I'm gonna come back here and I'm just gonna say f prime of x is 0 for this function. Okay, so now let's look at if it's not a constant and if it's just g of x equals x. So if I were to use my definition of a limit, so we would find the limit as h approaches 0 of x plus h minus x, right? There's f of x plus h, there's f of x over h. So if I were to simplify this, we'd get x minus x, which is 0, and then we'd be left with h over h, which is just 1. So g prime of x is 1. So anytime we have just f of x equals x, g of x equals x, okay? And sorry, this is a typo. This should be an x right there. Okay, so anytime we have this function, the derivative of that function is always 1. So we don't have to do this definition every time. We can recognize that pattern that it's always going to be 1. We actually have something kind of similar when I raise something to a power. So let's kind of we'll do our longhand definition and then we'll kind of hopefully see what the pattern is. So we're going to find the limit as h approaches 0 of f of x plus h, so that's going to be x plus h squared in this case, minus f of x, h of x, sorry, in this case, over h. Expand, so we get x squared plus 2xh minus plus h squared minus x squared all over h. My x squareds cancel. I can divide out the h's, and we're left with the limit as h approaches 0 of 2x plus h. Plug in 0 there, and I get 2x. Okay, so let's just kind of recognize, so this is h prime of x is 2x. Okay, so let's just look at how my original function compares to this. So basically the 2 ends up being the coefficient. And I mentioned this in a previous video, but my degree always drops every time I find a derivative. So if I started with a second degree, this goes to a first degree. So basically my power comes down as a coefficient, multiplying by this variable, and my power decreases by 1. So we're going to call this the simple power rule. So the derivative of something raised to the n power, we always can bring that n down as a coefficient, times x, and then my power decreases by 1. So whatever it is to start, we just subtract 1. So again, I can actually use this just to make it a little bit quicker to find the derivative of anything raised to a power and not have to do the difference quotient every single time. All right, so let's try those 3 rules. and find the derivative. Okay, so this is a constant, right? It's just a number. As soon as I see that constant, the derivative is 0. I could also write it like this: d dx of root 3 is 0, okay? All right, find the derivative here. Okay, so this is a power, so I'm gonna use my simple power rule. So g prime of x, I bring down the power as a coefficient, and I decrease my power by 1. So that would be my derivative of g of x. All right, another couple rules that are just going to be helpful when finding the derivative. So we're going to use those 3 that we just looked at, but anytime we have a constant multiplied by a derivative, we just can find the derivative and multiply by the constant. Some rules, so if we can break, if we have a function comprised of 2 functions, we can find their derivatives separately and then add them together. Same with subtraction. And then these last 2 are just ones that you guys need to memorize. So the derivative of e to the x is e to the x. So that one is kind of easy, nothing changes. The derivative of natural log of x is 1 over x. And again, you can look at the proof in your book if you want. You can use the difference quotient, that limit definition, to find it. But basically, you'll find that these patterns always hold true. So this is kind of a shortcut so we don't have to use that limit definition every single time. Okay, and this is another typo. This should say f of u. Okay, so we're going to find the derivative of each function. So in this one, because my variable is u, if I wanted to use Leibniz notation, it would look like this: d du. Okay, so if we're finding d du of f of u, okay, so what that's going to be is, all right, so we have this constant. So we can bring that constant out front times the derivative of u squared. So we know our simple power rule is bring that exponent down and decrease this by 1. So what this negative 1/2 does is it just ends up multiplying by this derivative. So we're going to get negative 1/2 times, bring down that 2, and then decrease the power by 1. And then I can go ahead and do negative 1/2 times 2 to get negative 1 u to the first. So my derivative of f is negative u. Okay, g prime, we can do the same thing. Okay, so this again, pi is a number, right? So we can actually kind of treat that as a constant. So we've got pi to the 4th, so we can just pull that constant out front. We're going to multiply that by the derivative of x to the 3rd. So this is a power. We can use that simple power rule. So we're going to keep that pi to the 4th times, bring down our 3 as the coefficient, and decrease our power by 1. And I'm going to leave it just like that. Maybe a little, we might put that 3 out in front, kind of just more traditionally, but we're just going to leave it as pi to the 4th in exact form. So that is our derivative of g of x. Okay, h of x. Okay, so we can, I'm adding 2 functions here. I can think of one function as 3x squared and the other is 8. So if I want to find the derivative of those 2 together, we can basically treat it like this. Again, I've got that constant multiple, so we can do 3 times the derivative of x squared plus the derivative of 8. So with addition, we can take the derivative of those 2 pieces separately and then add them together. So this first part, I can apply my power rule. So I've got 3 times, bring down the 2, decrease my exponent by 1. And then this is the derivative of a constant, which we know is always 0. So our derivative here is going to simplify to 6x. Okay, f of x, same thing, the sum. So I can kind of find this derivative separately. So we're going to do 4 times the derivative of e to the x plus the derivative of x to the 3rd. Okay, so we get, remember the derivative of e to the x is just itself. So we've got 4 times e to the x plus my simple power rule turns it to that. And then we can leave it just like this. There's no like terms to put together. So that is my derivative function. Okay, last one, g prime, okay, multiple, constant multiple times the derivative of the natural log of x minus 5 again is a kind constant multiple, and then we're going to multiply by the derivative of x squared. So we get 3 derivative of natural log of x. Remember, that's one we want to commit to memory, is going to be 1 over x. Minus, use my simple power rule, bring down the 2. Okay? Here, this is going to equal 3 over x minus 10x. If I were to get a common denominator and combine these, I would multiply this guy by x over x. So my g prime, or derivative of this function, would be 3 minus x squared over x. All right, that's it for 2.3-1.